Today's topic is the comb function of Fourier transform. Introduction to Fourier transform. The Fourier transform is a mathematical technique used to analyze functions in terms of their frequency components. This method decomposes a signal into its constituent frequencies, providing insight into its spectral characteristics. Understanding Fourier transform is essential for various applications in engineering, physics, and signal processing. What is a comb function? Comb function. A comb function is a periodic function consisting of an infinite series of Dirac delta functions. It is mathematically represented as a series of impulses spaced at regular intervals. The comb function is often used in signal processing to represent discrete sampling in the frequency domain. Mathematical representation of comb function. The mathematical form of comb function is given by text comb t is equal to sum n is equal to infinity delta t. Here t represents the period or spacing between the impulses. This representation highlights the periodic nature of comb function. Fourier transform of comb function. The Fourier transform of comb function yields another comb function in the frequency domain, specifically mathematical text complex. This shows that the frequency domain representation is also periodic, scaled by the factor. Properties of comb function. The comb function possesses unique properties including periodicity and scaling in both time and frequency domains. It is an ideal representation for sampling theory, allowing us to analyze how signals behave when sampled. The delta function in the comb function make it useful for deriving properties related to impulse responses. Applications of comb function. Comb function Comb functions are commonly used in digital signal processing, particularly in systems involving sampling. They are essential in the reconstruction of signals from their samples through interpolation methods. Additionally, comb functions are utilized in spectral analysis for identifying harmonics in signals. Relationship with sampling theorem. The sampling theorem states that signal can be perfectly reconstructed if it is sampled at twice its bandwidth. The comb function illustrates this theorem by showing how signals can be represented at discrete intervals. Understanding this relationship is crucial for developing effective digital communication systems. Inverse Fourier transform of comb function. The inverse Fourier transform of comb function reconstructs the original time domain signal. It is represented as mathematical f text comb nu is equal to t text. This demonstrates the bidirectional relationship between time and frequency representations. Visual representation of the comb function. Graphically, a comb function appears as a series of spikes or impulses at regular intervals along the time axis. The spikes represent the delta functions, emphasizing the discrete nature of the comb function. Visualizing the comb function aids in comprehending its periodicity and spacing properties. discrete Fourier transform and comb function. This discrete Fourier transform (DFT) is closely related to the continuous Fourier transform of comb functions. DFT operates on sampled data, making it essential for practical applications in digital signal processing. The comb function's behavior in the DFT context is vital for understanding frequency resolution. Discrete Fourier transform and filtering and filtering the filtering and the comb function. The comb function can be used to design filters that isolate specific frequency components of a signal. By applying a comb function in the frequency domain, one can create bandpass filters for desired spectral features. This filtering capability is particularly useful in various engineering and audio processing applications. Aliasing and the comb function. Aliasing occurs when a signal is sampled below its Nyquist rate, leading to distortion in the reconstructed signal. The comb function visually represents the effects of aliasing in the frequency domain. Understanding this phenomenon is crucial for effective signal processing and avoiding loss of information. Real-world examples of comb functions. Comb functions are used in telecommunications for pulse shaping and signal modulation techniques. In audio processing, they can help analyze harmonic content and synthesize sounds through additive synthesis. Additionally, they are applied in imaging systems for pixel sampling and reconstruction. Comb function in spectral analysis. The comb function allows for the identification of periodic components within a complex signal spectrum. It simplifies the analysis of harmonics and enables the extraction of fundamental frequencies. Spectral analysis using the comb function is widely applied in various scientific fields. Mathematical proof of Fourier transform of comb function. The proof of the Fourier transform of a comb function relies on the properties of delta functions and periodicity. By substituting the definition of the comb function into the Fourier transform integral, one derives the frequency representation. This mathematical approach solidifies the understanding of how comb functions operate in both domains. Limitations of the comb function. While highly useful, the comb function has limitations specifically regarding non-ideal sampling. Real-world systems may introduce noise, leading to inaccuracies in the reconstruction of signals. Understanding these limitations is essential for developing robust signal processing systems. Advanced applications of comb functions. Beyond basic applications, comb functions are used in advanced areas such as radar signal processing and telecommunications. They enable the analysis of complex waveforms and the enhancement of signal detection capabilities. Research continues into innovative applications of comb function in emerging technologies. Recent developments in comb function research. Ongoing research is exploring the use of comb functions in machine learning and artificial intelligence for signal analysis. New algorithms are being developed that utilize comb functions for improved data compression and feature extraction. This field continues to evolve, highlighting the importance of comb functions in modern technology. Future directions in comb function studies. Future studies could focus on integrating comb functions with other mathematical techniques for enhanced signal processing. Investigating the effects of non-linearities in real-world systems could lead to more accurate models. Collaboration across disciplines may yield innovative applications of comb functions in various sectors. Conclusion: the comb function is a fundamental concept in the Fourier transform bridging time and frequency domains. Its application in filtering and spectral analysis demonstrates its significance in signal processing. Understanding the comb function equips engineers and scientists with tools for effective data analysis and communication. Thank you.